Hi, geometry students, welcome back. So this is part 2 of lesson 3.4, and I am on page 84 of your student journals. All right, so we did kind of the constructions and we talked about kind of the behind the scenes type stuff, the vocab and so forth, for how to do this math. So what we're going to practice here in these 4 examples is how to find the distance from a point to a line. And so if you notice, we're finding a point A to line BC. So here's BC, here's point A. And if you remember from the last video, I talked about how in order to measure a distance, you want to make sure that this line, so the line that we connect from point A to the line BC, has to be perpendicular. So we're going to connect that perpendicular line down. So what they also did here, you notice how this kind of forms a triangle, right? So if this is perpendicular, we know that this triangle right here is a right triangle. And so if we know it's a right triangle, we actually have a couple options to be able to help us figure out the distance. We can use Pythagorean theorem or we can use the distance formula. So you have 2 points here. You can always use the distance formula. I'm going to show you how to use the Pythagorean theorem on this one, just so that you guys can have another option. So the first thing I'm going to do is I'm going to actually make this a little bit different. So I'm going to go ahead and, since I'm trying to find this distance here, I'm going to make a right triangle where the distance I'm finding is the hypotenuse of my triangle. So all I did is just kind of draw it over to the side there like that. So now what I'm going to do is I'm going to measure this. Pay attention to your scale. Make sure you're not just counting by ones, even though it's 2 squares, make sure it actually is counting by ones, which it is. So this is a distance of 2, this is a distance of 2. So I'm going to use my Pythagorean theorem. A squared plus b squared equals c squared. And then I'm going to plug in 2 for a and b, and c is what I'm solving for. So remember, your hypotenuse has to be your c distance. And so I get 8. Remember, you're finding the square root. It would be plus or minus 2 root 2 if you were going to write this in radical form. So obviously here we are talking about a distance, so we only want the positive version of this. So my final answer is 2 root 2. So that's one way of doing this. Let me show you another way. So we could always just use the distance formula. So on this example, we're finding here's BC and here's point A. So we're going to find the distance right here. So we're going to find the distance of A to D. This time I'm going to use the distance formula. So I'm going to start with this point and go to this point. So I'm going to use D and A. So remember, the distance formula, for those of you who don't remember, is x2 minus x1 squared plus y2 minus y1 squared. And then, oops, I'm off the page here. And then you take the square root of that whole thing. Okay, so I'm going to do 3 minus negative 3 squared plus 2 minus negative 4 squared. So 3 minus negative 3 would be what, 6? So 6 squared is 36. 2 minus negative 4 would be 6. So 6 squared is 36. So this is the square root of 72. So let's reduce this radical. Well, we already know that 36 goes into it, right? And we know the square root of 36 is 6. So this would be 6 root 2 as my final answer. Again, we're only going to take the positive version of that one because even though we have to put a plus or minus every time we square root, we're only talking about a distance on that one. All right, let's go on to the third example. Here's line BC, here's point A. Make sure you're finding the correct distance. If you're finding the distance you want, and this time we want the distance from A to C. So again, you can use, I'm going to go ahead and use Pythagorean theorem on this one. I'm going to drop this down and make this into a right triangle. And this is a distance of 2, and this is a distance of 4. And I'm going to solve for C. So basically all I'm going to do is use the Pythagorean theorem on this one. So I'm going to do 2 squared plus 4 squared equals C squared. And so that's 4 plus 16. So I get 20. Square root of 20 I know 4 goes into 20, so that's 2 root 5 equals c. It's actually not c. We're going to call it, it's a to c is the distance. So that's the length that we're trying to find. All right, the last one on this page, again, has us finding the distance from, here's line BC, here's point A, so we want this distance A to C. Let's go ahead and use the distance formula on this. Make this a little bit further back. All right, so I'm going to go 3 minus 1 squared plus 2 minus 3 squared. So 3 minus 1 is 2, 2 squared is 4. 2 minus 3 is -1, -1 squared is 1. So I get root 5. So that's what you're going to be doing when you're asking to find the distance from a point to a line. You're really just either going to use the Pythagorean theorem or you're going to use the distance formula. So just kind of a flashback from when we did this in, what was it, Unit 1, I think we did this in. All right, let's do page 85 together as well. So this one says, determine which lines, if any, must be parallel. Explain your reasoning. So they're trying to get us to use those theorems that we just talked about. So remember all the ones with like the parallel transversals and all that kind of good stuff? So this one talks about, so what I have here is a line is perpendicular to another line. So it says, in a plane, if a transversal is perpendicular to one of the two parallel lines, then it's perpendicular to the other. Well, the problem with that is we don't know that these are parallel lines. They're not marked as parallel. So we know that this is perpendicular to that one, but we don't know it's perpendicular to the other one. So I'm having a hard time with that one in terms of knowing whether or not that those lines would have to be parallel. Determine which lines, if any, must be parallel. So obviously only P and Q could look like they're parallel, right? And I don't know if I have enough information. So let's see if I find another theorem. So I was looking at the linear pair perpendicular theorem. No, I'm sorry. I was looking at the perpendicular transversal theorem. That's the one that if a line is perpendicular to one, then it has to be perpendicular to the other. But that's saying that you are given the fact that the lines are parallel to begin with. On the other, let me see if there's any other ones that we dealt with perpendicular. I don't believe so. So I'm going to go on and say that I don't think we have enough information to figure this one out. So I'm going to say there's none. All right, number 6. This is the one that I think kind of goes over that linear or perpendicular transversal theorem, right? In a plane, if a transversal, should say plane. If a transversal is perpendicular to one of the two parallel lines, then it's perpendicular to the other. So that one, again, kind of assumes that they're parallel. Hang on, let's do the next one. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Okay, so if two lines, so that's what we're going to use on this one. That's the lines perpendicular to a transversal theorem. So if I have two lines, so P and Q, are perpendicular to the same line. They're both perpendicular to R. So if two lines are perpendicular to the same line, then they must be parallel to each other. So now we know that P is parallel to Q. So the theorem that we're using here is lines perpendicular, I'm going to use my symbols here, to a transversal. And that's a theorem. Okay, let's go to number 7. So number 7 looks like I have, if we're trying to either prove M and N are parallel, so I should probably mention that P is parallel to Q up here. So do we know that if two lines are perpendicular to the same line? Well, M is perpendicular to J and N is perpendicular to K, so they're not perpendicular to the same line. Let's see here. K is perpendicular to M, and J is perpendicular to M. So I can say that J is parallel to K because both J and K are perpendicular to the same line. So I can say that one. And the theorem I'm quoting here are, again, the same one that we did up here. Lines perpendicular to a transversal theorem. So that one. I don't know if there's another way. So M is perpendicular to J, and M is perpendicular. Yeah, there's no other way to be able to prove M and N are perpendicular. Or I'm sorry, parallel. All right, let's go to number 8. Okay. S is perpendicular to M, T is perpendicular to N, so they're not perpendicular to the same thing. M is perpendicular to S, and N is perpendicular to T. And angle 1 is congruent to angle 2. All right, so if two lines intersect to form a linear pair of congruent angles, then they are perpendicular. A linear pair of congruent angles. All right, so this one right here, we have to use this theorem on, which is the linear pair perpendicular theorem. If two lines intersect to form a linear pair of congruent angles, so N intersects with S, and it forms a linear pair, so 1 and 2 are a linear pair, and they're congruent, then the lines are perpendicular. So then this line, so this would be perpendicular to this one. Okay, well, now that we know that, so we use the linear pair perpendicular theorem, now we can say S is perpendicular to N, and T is perpendicular to N, so T and S are parallel because they're perpendicular to the same one. M and N are both perpendicular to S, and I don't think we have a perpendicular transitive property, do we? Let me make sure I have one. Okay. So I believe that's the only one we can show here because we don't have enough information to be able to show that M is parallel to N. But we do know that S is parallel to T. So at least there's that. All right, that's it for the second half of this video. Again, if you have questions, make sure you ask your teacher and always practice your skills. All right, let me know if you have any questions. Bye, guys.